Hello and welcome back to the Calculus 1 playlist. In today's video, we're going to be talking about inverse functions, and specifically we need to discuss what one-to-one functions are, then talk about the definition of inverse functions and some of the cancellation formulas. And in the following video, the next one, we're going to be speaking about inverse trig functions. So without further ado, let's begin by defining one-to-one functions. Let's just underline this, one-to-one functions. So essentially, a one-to-one function is a function that for every x inputs, we have only one and only one output. So let's write down a definition for this. So for every x value, there is one and only one y value, meaning multiple x values can not have the same y value. Great. So a simpler definition of this would be that f of x1 cannot equal to f of x2 for all x. So we will never have one x value have the exact same value as another y value, as another x value. So how can we do this? This can actually be determined very simply using the horizontal line test. If you recall previously when we were defining functions, a function can be found. We can determine if some graph is a function by seeing if it passes the vertical line test. So let's draw some graphs. Let's draw the graph of x squared versus x cubed, v, so I can show you guys what I mean. Let's draw this one on this side and this one right here. So let's call this one x cubed and x squared. So recall, you should know that x squared graph kind of looks something similar to this, and x cubed would look something like this. So note, both of these pass the vertical line test. So they're both functions. We can say that both of these functions, or these graphs, are functions. So we can say that this is f of x is equal to x squared, and this is f of x equals to x cubed. Great. But the horizontal line test is what tells us whether a function is one-to-one. So for x squared, we see that we have, that's not a great horizontal line, but you get the point that we have two x values corresponding to the same outputs. So this is not one-to-one, since we have f of x 1 is equal to f of x2 for some values of x. So for example, to give you an example of this, you could say f of -1 is equal to -1 squared, which is equal to 1, and f of 1 is equal to 1 squared, which is equal to 1. So we have two different x values corresponding to the same output. So a function cannot be one-to-one. Whereas for f of x is equal to x cubed, we see that it does pass the horizontal line test. So not only does it pass the vertical line test, it passes the horizontal line test. So we can say that this is one-to-one. Since for all x, there is f of x1 does not equal to f of x2. There's no inputs that correspond to the same output value. So that's the definition of a one-to-one function, and that's how we can tell using the horizontal line test. So we know that then we can say that a function is said to have, spell that, to have an inverse only if it is 1 to 1. So if a function is not 1 to 1, it is impossible for it to have an inverse. So we can say that this function f of x is equal to x squared does not have an inverse, whilst f of x is equal to x cubed does have an inverse, since it is 1 to 1. Great. So how do we define an inverse? So an inverse can be defined as, so if we have y is equal to f of x, then we can say the inverse of f of x is equal to f of y. So in other words, if we have some function y is equal to f of x, by interchanging x and y values, we can find the inverse of f of x. So let's write that down. Interchange x and y values and solve for y. Great. So let's do a quick example of that just so that you can see what I'm referring to. And actually before that, it's important to note some notation. So notice we have this f of -1 to x. I just want to make it very clear that f -1 of x is not equal to 1 over f of x. So it is not the reciprocal function. So inverse is not a reciprocal. So a lot of times people get confused with this notation because of this -1 here. What a reciprocal actually looks like is f of x -1. So I'm going to put does not equal to. This is equal to 1 over f of x. And this is very important to understand because we don't want to mix up the two. An inverse function is not the same as the reciprocal of the original function. So let's look at a quick example, a pretty simple example for you. So example, and note I've already checked if this function is 1 to 1, so you don't have to do that. You could plot it out and do the horizontal line test, but yes, this function is a 1 to 1 function. So f of x is equal to x to the 5 plus 14. So we want to find f inverse of x. So again, as we said previously, we want to interchange x and y values, then solve for y. So we can say then that the inverse, f of negative of x, we would go by saying that this is x is equal to y to the 5 plus 14. So we interchanged our x and y values. Now we'll just solve for y. So isolating for y, we find that x minus 14 is equal to y to the 5th power, and taking the 5th root, we get that y is equal to 5x minus 14. Very straightforward. We interchanged the x and y values of our original function, then we solved for y. Great. So let's say we're given two functions and we want to check if a function has an inverse. What can we do with that? So how to see if a function its inverse. How to see? Let's write that better. Checking a function's inverse. Yes, that's better. So to do this, we can use something called the cancellation formulas. So cancellation formulas. So the cancellation formulas essentially just state that the inverse of the original function should give you x. And conversely, the function where we plug in the inverse of that function should also leave you with x. So these formulas basically state a relationship between a function and its inverse. And let's look at an example while doing this, because this is probably the easiest way to understand that. Let's say that I tell you that f of x is equal to x raised to 5. And I propose to you that the inverse of that function, f of x, f inverse of x, is x raised to 1/5. How do we know if this is true? How can we check if this is true? So we'll just plug in f of f inverse of x, and we'll see if that's equal to x. Let's see if the left-hand side is equal to the right-hand side. So we go f, and the inverse of x is x to the 1/5 is equal to x, and we know that f is x to the 5. So we go x to the 1/5 all raised to 5, and that needs to equal to x. By rules of exponents, we know that this is equal to x and this is equal to x. Left-hand side is equal to right-hand side. So this is true. This is true. And so we can say that if we have a function and its inverse, we can check whether this is a true relationship, whether by seeing if the function and its inverse give you, when they're composed together, we can see that they are equivalent to x. So this is an important formula, and we'll talk more about this in terms of logs and exponents. But yes, it's an important formula. Great. So another direct consequence of this is, let's say that I have f of 15, and I tell you that's equal to 3. Then if I take the inverse of 3, that should give me 15. Conversely, let's say I had a function f of 16 is equal to 12. Then if I say the f of the inverse function at 12, the value corresponding to that is 16. So this is a direct consequence of the cancellation formulas, that we can go back and forth using the functions and their inverses. And in fact, that we can say that this is, graphically speaking, we can say then that the inverse functions are symmetrical about the y-axis, or sorry, about the line y is equal to x. So what do I mean by that? Well, let's say we have this graph, and let's draw this line y is equal to x. Then if we have some function here, let's say this is f of x, then the inverse of f of x is just the mirrored reflection about the line y is equal to x. So this is f inverse of x. This is a direct consequence, again, of the properties of an inverse function and the cancellation properties, the cancellation formulas. So we can see that functions and their inverses are related, and graphically they're related by symmetry about the line y is equal to x. So I'm going to end the video here now. In the next video, we'll continue with our discussion of function inverses, specifically trig inverses, and see how we handle those cases. And yeah, if you enjoyed, please like, share, subscribe, and I'll see you in the next video.